Hi, folks. So two things we're going to do in this video. One, I'm going to finish up some stuff I didn't get to finish up with cohort 2. As I've learned this year, everything on Zoom is just that little bit slower. So I was not able to get all the way through everything I wanted to talk about. And then I'm going to do problems 12, 13, and 15 as sample problems. I'll make a clear delineation because some people might want to watch one part of this video but not the other. So just to recapture the main thing we said, we were talking about the law of conservation of linear momentum. And we said that that law says that the initial momentum of a system vector is equal to the final momentum of the system vector because in a situation where the net external force on the system is equal to 0 in that dimension vector, right? So that says that the only forces acting on that axis where we're conserving momentum are internal forces, forces between the members of the system. Now, in this class, we're going to constrain our system to be two objects at most, right? But that doesn't need to be true. I can do conservation of momentum between any number of objects as long as the only forces acting are forces between the members of the system itself as we define the system. So what does this mean practically? Well, what does initial momentum of the system mean? Well, that means the vector sum of all the momenta, plural for momentum, of the system before the interaction. And then PF is once again the vector sum of all the momenta of the system after the interaction. So really what we have to talk about is there are three main types of interactions which will then affect how we set this up. But no matter what, this is going to be the first thing that we're going to write down as a premise for doing these problems. And you see how I structure that. In the same way that we started force problems with F net x equals max, or we started a kinematics problem with like delta y is equal to VIYT plus 1/2 AYT squared. And then we did our work underneath. This is the premise for the problem. It tells the reader that I'm doing a conservation of momentum type problem. So like I said, there are three main types of interactions. Okay. And the first of those interactions, number one, is going to be something called a perfectly elastic collision. Right? Now that word elastic there is really important. What we had before functionally was a perfectly elastic collision with the two blue carts, because you had that springy thing in between them. There's your elastic, right? And the two objects bounce off one another. And that's going to be the main visual aspect of this. So two objects bounce off each other. Once again, it doesn't have to be two objects. It could be 50 objects bouncing off each other, but we're constraining our conversation to just small numbers of objects just because we're getting used to the concept. So we start with two things before the interaction, and then we have two things after the interaction. That's what that's going to look like, okay? So what does that mean? Well, when I do PI of the system is equal to PF of the system, because the F net external on the system is equal to 0, I'm going to have the initial momentum of object 1, vector, initial momentum of object 2, vector, is equal to the final momentum of object 1, vector, plus the final momentum of object 2, and then it becomes an accounting problem. I have my before and after pictures, and I fill in as appropriate, as we will see, okay? And we'll see that in the sample problems. So I'll just make a note here as well. I know it says perfectly elastic collision. There's actually a distinction in physics between a perfectly elastic collision and an elastic collision. We are not going to deal with the distinction between that in this class. In our next unit, I will describe that distinction, but we're not going to do problems with that distinction. So all of our elastic collisions are going to be perfectly elastic collisions. So when I say perfectly elastic and elastic, we're going to use those as synonyms, but we are recognizing right now that because of where we are with this, that there is actually a distinction between them, a slight distinction. And I'll tell you what it is later. All right, going on to number 2. We're going to have make sure that's on the screen, perfectly inelastic collision. Well, what's going to happen in these? These are going to be collisions where two things collide and then they stick together. Think of like a wet slab of clay hitting someone's head, right? Or someone does a flying tackle and grabs someone else, right? So what the main thing here is we have two objects sticking together. So we start with two objects beforehand and we end up with one object afterwards. So when I do my PI of the system is equal to PF of the system. Now, by the way, I should have vector symbols over those. We're not going to write them when we're doing problems. I'm just emphasizing now that it's very important that they're vectors. So I'm just going to put them in now. And when I do the problems in a couple of minutes, you're going to notice I don't do them because the F net external on the system is equal to 0. So I have two objects beforehand. So initial momentum of object 1 plus the initial momentum of object 2. But after the interaction, I only have one object. So it's the final momentum of the combined object. So combo, I'll just call that there, right? Two terms before the interaction, one term after the interaction. All right, so there we go. The third type of interaction is going to be kind of the opposite of the inelastic collision. Rather than having two objects stick together, what happens if I have one object that blows apart, right? Like, for example, if I have those two blue carts and I smush them together and then I let go, they pop apart. The classic example here is a bullet and a gun. So initially, the bullet and the gun are one, right? And then the explosion happens and they go in separate directions. So here, we're going to call these explosions, or as they're sometimes called, recoil interactions. And here we have one object breaks apart into two. Now, it doesn't only have to be two, once again. It could be multiple objects, but we're constraining our conversation to make it easier, right? So we have one object before, two objects after. And so what does that look like? Once again, PI of the system is equal to PF of the system because the net external force on the system is equal to 0. I'm writing it every single time. And so initially, I have the initial momentum of the whole thing. I'll just call that PI all, I don't know, whatever works, is equal to PF of object 1 plus PF of object 2. Boom. And that's how I do those things, right? The important thing here is if I know the two objects stick together in the perfectly inelastic collision, that means VF1 is equal to VF2, right? Which is why I can do this combo mass. And here, if they start as one object, that means that VI of 1 was equal to VI of 2, okay? And obviously the perfectly elastic collision is when nothing's equal, right? So that is how we're going to do these problems. That's the major last distinction. In the next unit, we'll talk about a couple more real important things about perfectly inelastic versus perfectly elastic collisions as well. So here's where we're going to transition to doing some problems off of the momentum sheet. So we're going to start with number 12. So I'm going to pull that up so we can see it. Number 12. So number 12 has a 3-kilogram rifle, has an 18-gram bullet loaded in it. The bullet leaves the barrel of the rifle with a velocity of 600 meters per second north. What's the recoil velocity of the rifle? And if the interaction lasts 0.002 seconds, find the average force that the explosion exerts on the bullet. All right. So this is an explosion type problem. So let's start with a picture, right? My before picture. My before picture is bullet and gun. Here it is, right? There it is. And so I'm going to call the gun mass 1 and the bullet mass 2. We know that mass 1 is equal to 3 kilograms and mass 2 is equal to, what was that? It was a certain number of grams. Was it 18 grams? It was 18 grams. So I'm going to make that into kilograms, 0.018 kilograms. Okay. And I know the initial velocity of object 1 was 0 and the initial velocity of object 2 was 0. And then boom, the gun goes off and the bullet goes north, I'm just going to, on my picture, make north to the right. So this way is north, and I'm going to make north positive. Okay, and so that is VF2. That means that there is some sort of VF1. I'm just presuming that it's going to go in that direction. Okay, now I know VF2 is equal to positive 600 meters per second. And so from here, what I'm going to do is I'm going to set up my conservation of momentum. So I know that PI of the system is equal to PF of the system because the net external force on the system is equal to 0. Now let's talk about that practically. I'm not drawing anything attached to the gun, but that's probably silly. There's probably someone holding the gun, right? So you may say, like, what? So there's a net external force because the gun is constrained. Well, not if you do it right. If you fire a gun correctly, actually, so here's my, finger gun. When you fire the gun, boom, what you're supposed to do is have soft hands and let that recoil happen. Otherwise, some really bad things happen. And we'll talk about those when we get together. Anyway, so I can presume that that force of the hand on the gun is not really impactful, so I can make this statement. Also, once again, this is intro physics, and we are simplifying. So here we go. I'm going to go initial momentum of object 1 plus initial momentum of object 2 is equal to final momentum of object 1 plus final momentum of object 2, right? Or I could have done P initial of the gun bullet system, right? But if I look at this, so that's mass 1 VI1 plus mass 2 VI2 is equal to mass 1 VF1 plus mass 2 VF2. I know that that's going to go to 0 and that's going to go to 0. So this entire side zeroes out, and then I can just plug in. So this is 3 kilograms times VF1 plus 0.018 kilograms times positive 600 meters per second. When I solve that, VF1 is equal to, let me just go to my calculator here. I get a negative 3.6 meters per second. And I look at that, and that makes sense to me. It's a recoil reaction. That's the left or really south, yes? And that makes sense that there's a kickback on that gun, so that momentum is conserved. Because initially, if we think about that, the initial momentum of the system is 0. That means that the final momentum of the system is 0. Has to be. So here's the interesting thing with momentum being a vector. Even though each object finally has momentum, the vector sum of the system has to be equal to 0. So you could have, and that's sort of a weird concept, and I want you to hold on to that in a system, you could have multiple things moving, right? So each individual object has a non-zero momentum, but the system has a 0 momentum. All right. So there we go. So that's my answer to this. And it makes sense, by the way, that the final speed of the bullet is less than the final speed of the gun is less than the bullet because the masses are different like that. And so let's do the B part of this. So if I want to know what the force on the bullet is, here I'm going to say the net external force on the bullet, so that's mass 2. Well, that's going to equal the change in momentum of the bullet over the time period. And so what do I have there? Well, that's P final 2 minus P initial 2 over delta T. And so what do I have there? P final 2 is going to equal 0.018 kilograms times 600 meters per second minus 0, stealing that from before, all over that time period, which we said is, I don't remember, 0.002 seconds, 0.002 seconds, and I can put that in my calculator. Okay. And find out that's a positive 5004 Newton force, right? And so that force must be to the north on that bullet. Okay, so there we go. Problem 12, a recoil type problem. So moving on, let's look at problem 13. And we're going to hopefully figure out that there's 3 problems and there's 3 problem types. That's what we're doing here. Problem 13, mass A is traveling west and collides inelastically with mass B. So here we go, mass A is traveling west. So we'll make west to the left. So here's A, okay. And so here's my before picture. So this is VIA, and mass B is traveling to the east. Okay, so that's VIB. Most of you are probably going to make to the east positive, so I will as well. So there we go. So let's get our information here. I've got mass B is equal to 30 kilograms. And because I made to the east positive, VIB is a positive 4 meters per second. Okay. Let me go back to my here, right? Mass A is equal to, and here's short attention span theater. I already forgot what the number is. 10 and 8. Okay. 10 kilograms, and VIA is equal to -8 meters per second. Okay. So that's what our scenario looks like. And we're told they collide inelastically. So that means that BA as a combination are going to have to go in some direction. So just stop for a second and try and predict what the direction that the combined mass is going to go. All right. Now, there's an argument to be made for both things. Some people may say, oh, well, it's going to go in the direction that B is going initially because B has a larger mass. And some people might say, well, A is going faster. Well, the truth of the matter is, and it doesn't matter which has a larger mass or which has a larger speed. What matters is which has a larger momentum initially. And just by inspection, it looks like B is going to have a larger momentum. So I'm just going to guess that here is the final velocity of both of them. It doesn't matter. We're going to prove mathematically what that is. I just like to do that little predictive thing beforehand so that we can sense check our answer. So once again, I'm going to start with the initial momentum of the system is equal to the final momentum of the system because the net external force on the system is equal to 0, right? Start with our premise. Now here I'm going to go PIA plus PIB. I'm dropping the vector signs once again because it's just annoying to write. And I'm just going to make this PF of both final. I'm not going to have separate terms for them final since they go off together. So what does that mean? So this is mass of A, initial velocity of A, mass of B, initial velocity of B is equal to, well, that's going to be the combined mass of MA plus MB and VF of both. And from here, once again, it's an accounting problem, pretty straightforward and easy, right? As long as you set it up nicely so that you can put the right things in the right places, these problems end up being pretty straightforward. Okay, it's equal to 30 kg plus 10 kg VF both. And so there we have it. I've got this -80 plus 120 is equal to 40 VF both. And then we do the math. We find that VF both is a positive 1 meter per second. So that is to the east. And that is the answer to part A of this problem. Okay. So let's go to part B of this problem. And it asks, or I ask, what did I ask? Oh, change the momentum of A, change the momentum of B. Awesome. So delta PA is going to equal to final momentum of A minus final momentum of, or their initial momentum of A. Now, here's something that people have a problem with during these inelastic collision problems. Just because A has sort of like combined with B after the collision doesn't mean that when I'm calculating the final momentum of A, that I take into account the mass of B. No, even though B, or the A is part of B, this is only talking about the A part of that. So what does that mean? So this is still mass A, final velocity A, and this is still mass A, initial velocity of A, right? So even though it's combined into some sort of overall blob, I don't account for that when I'm doing this impulse type calculation. So let's just plug in there. So mass of A, we said, is 10 kilograms. Final velocity of A is positive 1 meter per second because it's part of the larger grouping. which all has a velocity of 1 meter per second east. And then notice here, I'm just going to steal that work from before because I actually already know that number. It's negative 80 Newton seconds. That's why I calculated that in that last step. I'll have you remember that I just found those numbers here because I wanted to be able to steal them for later parts of the problem. So I did that here. And so when we do that, we find this is a positive 90 Newton second impulse, and that is an eastward impulse. And that should make sense, folks, because A is going to collide with B, right? And so the force is going to be on A to the right or to the east. So it makes sense that the impulse is to the east. C, delta P, B. Similar argument, PFB minus PIB is equal to mass of B, VF of B, minus mass of B, VI of B. So this is 30 kilograms times that positive 1 meter per second. I don't know why there's another parens there, minus, and I'm going to steal that number from before, 120 Newton seconds. And so that gives us a negative 90 Newton seconds, and that is west. And that makes sense once again, because if these two things collide, B is going to be pushed to the left, which is west. Now, also notice here, oh man, of course, the amount of momentum gained by one has to equal the amount of momentum lost by the other. That's required by Newton's third law. And I could have leveraged that here. I could have just done C like, delta PB has to equal negative delta PA because of Newton's third law. And I could have just asserted that answer right there. But I wanted to show the calculation. In fact, I think it's a really good idea to do both these calculations because if you did the problem right, the momentum problem right here, conservation momentum problem right, those two can function as your check. So that's always a good thing. I like a good check. What's the impulse mass A experiences? Well, this is me once again ensuring that you know the impulse has changed in momentum. I'm just going to change that to B and D and be done with it. And then finally, if the collision lasts for 0.6 seconds or 0.06 seconds, find the net force on mass A. So the net external force on A is going to be delta PA over delta T. And so that's just grabbing my numbers plus 90 Newton seconds divided by 0.02 seconds and then throwing my calculator. That gives me positive 4500 newtons, and that is, of course, east there. So all of that makes sense, hopefully. Oh, six, not 2, making this 1500, excuse me, east. Okay, cool. And then our last problem that we're going to do here is number 15. So I've got a 5 kilogram ball is moving to the right when it collides elastically. So trying to make sure we cover all our bases here. So the first thing I'm going to do is I'm going to name the 5 kilogram ball number 1. It's moving to the right, so VI1. And then we have our 2 kilogram ball, which I'm going to name 2. It's going to the left, VI2. And then they collide elastically. And so finally, the 5 kilogram ball, which is 1, is going to be still moving to the right, so VF1. And I want to know what's happening to 2. So that's my before and after picture. Okay, so let's get down the information. We know mass 1, we know mass 2. So before I actually get down the information, let's make to the right positive so that we can write down our information the first time with our declarations. So mass 1, once again, was 5 kilograms. Mass 2 is 2 kilograms. We know VI1 is a positive 4 meters per second then because of our declaration, and VI2 is a negative 6 meters per second. We know VF1 is a positive 0.8 meters per second. So I'll just go back to our diagram there, and that's what I have. So I want to know what VF2 is. I'm going to assume VF2 is to the right because it kind of just makes sense. Otherwise, it's going to have to travel through mass 1, which would make no sense. So PI cis is equal to PF cis because the net external force on the system is equal to 0. So I'm just going to do PI1 plus PI2 is equal to PF1 plus PF2, kind of construct. I know I have 2 things before, 2 things after. So M1 VI1 plus M2 VI2 is equal to M1 VF1 plus M2 VF2, and then let's do the accounting problem, right? 5 kilograms times times positive 4 meters per second plus 2 kilograms times a negative 6 meters per second is equal to 5 kilograms times a positive 0.8 meters per second plus 2 kilograms times VF2. We'll figure out what that is. Now, I'm just going to look back at the problem. Okay, I'm going to want to know the impulse on the ball. So actually, I'm going to do some intermediary calculations here. 20 minus 12 is equal to 4 plus 2 VF2, right? Because I'm going to be able to steal some of those numbers. And I don't do this step unless I know there's a part of the problem where stealing those numbers is helpful. So doing the math here, I get 8 equals 4 plus 2 VF2. 4 is equal to 2 VF2. Okay, so VF2 is equal to a positive 2 meters per second, and that is to the right. Awesome. And so now I want to know what the impulse on the 5 kilogram ball is. So that's delta P1, and that's PF1 minus PI1. And looking at that, I've already calculated those numbers, so I can steal the 4 there. So 4 Newton seconds minus 20 Newton seconds, and that gives me negative 16 Newton seconds. And I am done with that. So sometimes stealing the work is a really great thing to do, and thinking ahead to, do I need to do these intermediary calculations so I can steal the work? So that's how we do these problems. You're going to do 14, 16, and 18. Once again, there's a recoil, an inelastic, a recoil, an inelastic, and an elastic, harder than you think to say, problem for you to do for this afternoon. So there you have it. And I will stop this recording if I can find out where that is. I have too many windows opens. Oh, here we go.